My name is Lillian Wilson-Wade, and today I'll be discussing my observations from Lab 2. In Lab 2, we had the task of observing the motion of an object falling slowly straight down. We needed to examine the drag force and its effect on the object's motion, and we also had to compare the observed data to predicted models, accounting for both just gravity and for gravity and drag. Some key concepts in this lab included Newton's second law, which will be useful in updating velocity in our model's calculation loops, also how to derive displacement from the change in velocity, which will help us update position in our model, and finally, the general calculation of net force when we're accounting for various forces. In the experimental model, I chose a plastic shopping bag as my system. The lab called for the falling object to fall slower than a rock, so I decided the bag would be a good model because its lightness will allow air to offer greater resistance to its falling, and its shape also allows it to kind of catch more air than a solid object. After using Tracker to track the motion, I received this parabolic graph representing the time versus the y position. I mentioned earlier that understanding how to calculate net force while accounting for various forces is key to this lab. The two forces we're accounting for in this lab are gravitational force and drag force. Gravitational force can be calculated by multiplying the mass of the object by the gravitational constant, 9.8 meters per second squared, by a unit vector. The drag force is also known as air resistance, and it acts opposite to the force of gravity, which is in the same direction as our relative motion. The drag force is proportional to the velocity squared by some constant, which is represented by b. To calculate the net force, we add these two forces together. In the calculation loop for the model accounting solely for gravity, we can disregard the drag force. The gravitational or the weight force can be calculated by the method I mentioned before, and being the sole force, it's equal to the net force. This model would represent the object falling in a vacuum, which would be a place with no air to exert any force on the object. In the calculation loop for the model accounting for gravity and drag, we calculate both the gravitational and drag forces and add them together to receive the net force. I found the proportionality constant b by trial and error until the final predicted y value matched the one in my observed data. When comparing the position versus time graphs, we can easily see that the model accounting for both gravity and drag is a better representation of my observed data. It's clear that the drag force played a large role in the object's motion because there is such a difference between the observed data and the gravity-only model. The model accounting for drag does differ from the experimental data in the middle, but this can be accounted for by imperfect testing conditions like wind or other forces that could affect the data. When I examined the velocity versus time models predicted by my models, I could see that in the model without drag, velocity continues at a constant rate which is equal to the rate of acceleration, 9.8 meters seconds per second. Like I said before, this model would represent the object falling in a vacuum, so it makes sense that it would never reach terminal velocity because the change in velocity would be constant and increasing. In the model accounting for drag, though, the model reaches a terminal velocity at the point where the gravitational and drag forces are equivalent, or when net force equals 0. The change in velocity at that point is 0, and the velocity is constant, so that's when the terminal velocity is reached. When I accounted for a change in the object's initial velocity, I found that it doesn't affect the value of terminal velocity. However, the object will reach terminal velocity more quickly because when you throw the object down initially rather than dropping it, thus starting with an increased initial velocity, the object is actually starting at a velocity that's closer to terminal velocity, so it's just going to reach it quicker. In conclusion, it's pretty evident that the drag force had an effect on my system. This lab as a whole also shows the importance of accounting for all forces when attempting to determine net force.